Able to see my screen? Just trying to make sure.
Yes.
Great, thank you, Will. And thank you, Eddie. And last time where we reach is chapter 6 at the tail. So let's kind of just review, what we have learned the last time. So last time we actually learning the special numbers, and so there's a type of the Mersenne primes, and this type of the prime is actually closely related to perfect number. So perfect number could be actually related to this form. And then we have Fermat prime. Fermat prime only like have limited number. Or originally people think they are unlimited of those, but only like first 4 and 5 of those are Fermat prime. And after that, those are not. Then there are twin prime and conjectures related to those fun stories. And then we have factorial that defined by this way, and perfect abundance and deficient number. And today we are going to cover the palindrome. And palindrome is just a fairly well-tested battleground in the AMCs. And so yeah, palindrome mostly can be used like using the counting technique. So the first problem is actually very simple. I just find the number of the 2-digit palindromes. Palindrome basically are numbers that are reading back forth the same way. So if it has 2 digits, for example, if it begin with 1, and so the second number has to be 1, because when you read this way and reading this way, it's going to be the same. Reading from left to right, the leading number is 1. Then leading from left to right, right to left, and you still need to be 1. So 1 here, guarantee 1 here. So basically, just by this standard, 2-digit palindrome need to have 2 identical numbers. So they are like number actually 9 of those. And how many 2-digit number are prime? Obviously only 1. So that's 11 is a single one that possibly will be the prime. And then this is actually doing the 3-digit palindrome, starting with 100-digit of 1. Then you start with 100-digit 1, then it's guaranteed. This is 100, tens, and the ones. That's guaranteed. So you read this way is 1, whatever. But when you're reading this way, this 1 will be here. So basically, it's when you lay down, the first digit is 1, then you actually lay down the ones position also as 1. So you lay down actually 2 1 simultaneously. And then if you lay down 2 1 simultaneously, there's only wiggle room for the 10th digit, which is allowed to be 0 all the way to 9, which is 10 numbers by the counting method. And then if you do it the same way to the digit of 2, you lay down 2 of the 2 at the same time, then this is also like 0 to 9, have 10 of those. Then you just consider the first digit, 100, you only have 9 ways to lay down number, because you can lay down from 1 all the way to 9. So actually 9 multiplied 10. So that's the counting, multiplication rule. So that's 90 of those. So, you actually can expand this problem a little bit more. For example, how many 4-digit, like palindrome can you have? Let's just ask this question by calling out names. Angela, can you answer the question? How many like total count of 4-digit palindromes do you have?
So do I just read the question?
You don't have to read the question. I'm asking a different question. So just expanding the scope. If we are doing a palindrome have 4 digits, so how many possible ways can you have this palindrome. It's a 4-digit number, start with 1,000. So the 1,000 cannot be 0. And that's the only restriction. And given that restriction, 4-digit palindromes, how many possible arrangement can you have? Okay, let me give you like 1 minute to think about it. Trying to think this against. So let me give you a hint. This is 1,000 position, this 100 position. This is the 10th position. This is the 1's position. So how many way to lay down the 1,000 position number, Angela? Thousand position. Let me just give you a more hint. Are you able to lay down 1?
Yes.
That's good. Are you able to lay down 0?
No.
So you are able to lay down 1, 2, all the way to 9. So how many total possible way can you lay down on 1,000 position?
9.
9 way, yes, exactly. So when you lay down 1, the 1's position is guaranteed to be which number?
1.
Yes, exactly. Palindrome have to go either way. And so how many way you lay down 100's position?
10.
10 way, exactly. You are able to 0 to 9. So when you lay down 0 here, for example, what number is guaranteed on the 10th position? When you, for
0.
example, yeah, 0. So basically, to lay down a 4-digit palindrome, you only care about, the 100 position and the 1,000 position and 100 position, is that right?
Yeah.
So the cardinality of 1,000 position is 9. Cardinality of 100 position is 10. So 9 multiplied 10 equals to 90. So, so basically the total count of all the possibility for palindrome for 4-digit is still 90. Do you see that? And so like, obviously 1-digit palindrome, one digit number, any number is actually palindrome if you consider it. And if say that we consider all the counting number, not including 0, you actually have 9 of those. And if we consider 2-digit palindrome, you also have 9 of those from 11 all the way to 99. So then 3-digit, you actually have 90 because that's 9 multiplied 10. You worry about 2 position. And then 4-digit, you also just worry about 2 position. It's 9 multiplied 10, also equal to 90. Then let's try to just expand this a little bit, like calling another name, Eddie. Let me just ask you that if I have a 5-digit palindrome, how many possible arrangements do you have? Eddie, can you unmute yourself and try to give this problem a try? Eddie, are you having technical difficulty? Looks like you are not. Okay, looks like Eddie has technical difficulty. Let's, Blair, would you give that a try? Blair, are you there?
Yeah.
Yes, give it a try to see that if you have a 5-digit palindrome, how many possible arrangements do you have?
So the first digit can be any digit from 1 to 9.
Yes.
Then it can't be 0. So basically also 9 choices for the second number. Oh, sorry. 9 choices for the first number and the fifth number. And then
Yes.
second digit, that would that number can be 0, so it would be 10 choices.
Yes.
And then for the third digit, there are also 10 choices. So basically that'd be 9 times 10 squared, which is 900.
900 exactly. You actually got it. Very good reasoning and very good answer. Thank you. And so that's about the depths of, so the number count of palindrome is actually a well-tested thing. You kind of just naturally, it's always, the first digit, not considering 0, it's 9 way, 2 digits 9 way, 3 digits 90 way, 4 digits 90 way, 5 digits is 900 way, and 6 digits still 900 way. So it's always kind of like, like the odd even adjacent one, like starting from odd 1, 2, as a group, they actually have the same count. Then 3, 4 has the same count. 5, 6 has the same count. So it always goes this way. So that's the way, you count and you only need to count, up to the middle, because, if, for example, 5 digit 1, 2, 3, 4, 5, and then basically you only need to count all the way to middle, because counting backward, it's already decided. When you lay down the first number, the last is simultaneously laid down. So basically that's the way you really do it. Okay, so we get over this topic. And this type of problem, and problem 11, 611 is actually, it's talking about how to factorization of this, then how to find 2 positive 3-digit palindrome, that product to be this number, and what is their sum. So this type of the problem, you actually focusing on the prime factorization first. For example, how to factorize this one. This is 9, 3 plus 6 is 9, 4 plus 5 equal to 9. So we know this number is divisible by 9. That's for sure. Then that's the first hint. The second hint is that the last digit is 5. So basically, it's divisible by both 9 and 5. So it's divisible by 45. So we can, when you factor down a big number, you want to factor down quick. So you kind of just do the 436,995 divided by 45, because that can factor down quicker, a little bit quicker. So this looks like I need to put up a 9 here. That's 40 here. So this is 1319, and 319 looks like I need to put up a 7 here. And so we got 49, another, so that's 1, and then 45, and then 45 again. Then that's, so basically we actually got 9711 as, another factor. So here, basically we factor down the like 45, multiply, and then we obviously this one is divisible by 9, so we put a 9 again, and this is basically going to be 63 and 81, so 10. So basically multiply 9, multiply 1079, and 1079, then we will trying to see, obviously it's not divisible by 2, 3, and 5. So next one we're going to try is going to try the number of like 7. So if 7 works or not. So 1079 divided by 7, and 37. That's going to be 29. It wouldn't work. So then we were going to try the 91079 divided by 11 wouldn't work. So we have to try 13. Then when trying 13, we are able to get to the this we can try 8 and 104, that's 39, so 83. So basically we are able to factor it out. 1079 is 13 multiplied 83. And then we actually is able to, factor this out. And this is actually 5 multiply, and this is a 3 to the 3 square. This is another 3 square. So basically it's actually 3 to the 4th. So this is the factorization of the whole thing. And then it's asking for palindrome, product of palindromes. Then basically this type of thing, fastest is trying to looking for the largest prime factor, which is 83. Because we know that 83 multiplied 13 is like a 4-digit number already. So, I need to pair the 83 because we need to find 2 palindrome product to this one. Then 83 pair with 13 obviously will not work. Then the number smaller than, given the factorization, if we have a 5 multiplied 3 equal to 15, it's even to be bigger. So smaller than 13, the next smallest one will be 9. So if we do the 9, so 83 multiply 9, yeah, 747. So this began to work. So if we 83 pair with 9, so we actually have 83 pair with 83 pair with 3 squared. So this is the first palindrome, which is 747. Then the remaining factor is actually 3/4, taking away 3 square. So you have 3 square left. Then you also have a 5. Also you have a 13. So those are the remaining factor that exists in this prime factorization. Let's see if that will make another palindrome. And so we have this 45 multiplied 13, which is 135 this way, and that is 45. And this actually make a palindrome, so 585. So if you add them up, and you're going to, because it's asking for find the total, it's going to, what is the sum? What is sum of those 2 positive 3-digit palindromes that product to this one? So basically I find the 2 factor which will be palindrome, and we add them up, going to be 13 and 1332. So that's the way that we can solve it. And yeah, this one looks very daunting, but if you just factor it out, then trying to pivot around the biggest prime, and also given the information multiplied by 13 is already 4-digit number, then you have only very limited option given the other prime factor is 3 and 5. So basically you pretty much all forced to try the next one is 9. And so that's just using the guidance of factorization actually will reduce the count of trying, because it's really hard to find that one palindrome. But if you know how to try, let's make it easy. Okay, so let's get to the next chapter of the topic. So the topic of this one is just dealing with the number serial problem. So number serial problem actually not necessarily appear as the number series itself. And a lot of time also coupled with a lot of geometry problem. So we actually have to know how to handle. So blend in the, algebra problem together with this. So this one is that let's trying to do this one. And so this problem, let's see that Will, can you try to read this problem?
Okay, let the tens digit of a two-digit number be A, and let its units digit be B. This two-digit number is equal to 3 times the sum of its digits. So it's gonna use the given information to write an equation with variables A and B. So it's the tens digit, so it must be. Oops, I'm in touch screen. Need better touch screen. I mean, I need to write better with a finger. Okay, anyways, 10A plus B is equal to 3 times A plus B, which is equal to
3 times the sums of the,
A
yeah,
plus
3B, that's better. Yeah.
and simplify your answer to get m times n, okay, for relatively prime natural numbers m and m. Whoops. Okay, so now we divide this, and this will become 2b. No, at the right we subtract. We subtract this as well. This will become 7a.
Yes.
So there.
Yes.
Say about the prime factorizations of a and b. A must be divisible by 7, and A must be divisible by 2, and B must be divisible by 7.
Yes.
What two-digit number is 3 times the sum of their digits?
I think you actually did very good until
The
this
answer
point.
is 27.
You're right. Yeah. A is 2 and B is 7 because at this point you actually have a restriction. Very good. I think Will, you actually did very good. So basically you kind of just represent this problem with the algebra and you reach the conclusion that 7 A is equal to like 2B. So basically, and we also has the restriction that A is greater, A basically need to be greater equals than 1 and less equals than 9. And then B will be like greater equals than 0 and less equals than 9. So basically these are the restriction applied to this integer function or integer equation. And given this, also we actually because there's a 7, so B is 7 multiple and B is 7 multiple, and so B was forced to be 7. B has to be 7 because 2B is product of 7, is multiple of 7, and B is also within the range of 0 and 9, and so there's no other way you can find another integer that is multiple of 7 at the same time less than 9. So less equal than 9. So basically B is forced to be 7. Then you actually calculate the right hand side out 14 and A will be forced to be 2. So basically 27 is the result. Awesomely done. Thank you. And so let's try the second problem. And so second problem, Xinlai, could you try to read this problem and give it a try?
Find the expression a squared minus b squared. Factor the expression a squared minus b squared.
Yes.
So I believe like something like a squared minus b squared would just turn into this.
You're right.
So that solves the first one. And find two distinct positive integers that have a product of 49.
Yes.
Well, I think the only ones here is 1 and 49, because 49 like is just 7 times 7, right? And there's no other ones that are, at least none that I know of, that are distinct or different.
Yes, 149 is the only choice. Yeah.
What is the sum of the two distinct counting numbers whose squares differ by 49? Well, I guess we just add a 49 back here, I guess.
Yeah. So this type of the equation, because you actually, this is an integer and these are integer, is that right? And those are integer with this restriction. So it has to be one of their prime factorization. So a plus b has to be 49 and a minus b has to be 1. So this is the way you,
yeah, I guess.
yeah. So basically the way you do it, a plus b equals to 49 and a minus b basically equal to 1. Then you adding them up to a equal to 50 and a going to be equal to 25. Then you do a minus between them, basically to b equal to 48 and b equal to 24. So basically you can actually do this way. And then you can double check it. Actually, double checking it actually not difficult. Basically 25 squared is 625. Then when doing the like do a minus, so 24 squared, 24, 90, so that's 488, 6. Yeah, 576. If you do a minus, that's going to be 49. So basically it all checks out. So that's the way. And even you consider, if the, it's possible to use 7 and 7 as a factorization. Then basically, a plus b equal to 7 and a minus b equal to 7. And if you do it this way, that 2a equal to 14, a equal to 7, then the other one basically 2b equal to 0, b equal to 0. So basically, the other one basically, is actually 7 and 0. 7 and 0 works in certain way, because 7 is just 49. 7 squared is 49 minus 0 squared is still 49. But the question is asking that counting number, and 0 is actually not a counting number. Counting number start from 1. So basically, the only answer is like 24 and 25. Those are the only two numbers that could be. Okay, let's go to the next problem. Xinlai, could you get rid of the character here? Otherwise, it's going to interfere with the screen next one. Yeah, okay, thank you. So this is actually a very, very important problem. This problem is very, very difficult. Problem 7.3, you actually has to totally get familiar with this type of technique. And so let me just show how to do it. And this problem actually, it has a special name for it. Problem 7.3 is actually called, let me see, what do they call it? Problem 7.3 actually using a technique called Simon's favorite factoring trick. So basically that's Simon factoring trick is named for this person called Simon Rubinstein. an active member of Adolf, problem solving online community. So basically this one, he actually, obviously is just a math lover. And so even you participate in a math community, just contribute a lot, then people might still remember the name. I don't know how why the name of this trick is being used, but at least in the Adolf problem solving communities, it's always been called like Simon's favorite trick. So if you're able to come up with something fun, and you still might leave your name on the math history, and that's kind of exciting thing. And so let's see that how to solve this problem. This problem is actually extremely difficult because we are trying to find that two number. This is an integer, two positive integer, that x and y, their reciprocal will add up to 1 out of 7. And we will x and greater than y, we will try to find the greatest possible value of 1 over x. So this problem, basically, when you look at this problem, you don't even know where to start. That's kind of how daunting this problem is. But since I already know the tricks, actually I know a fixed way, a very consistent way to do it. I'm just going to show the trick, because obviously the first people doing it, Simon is very smart. So basically, just kudos to him. And so the way to do it, first, we're going to do the just the normal thing, that when you're dealing with this type of equation, what we call is called rational equation. So the standard rational equation, when you deal with it, is actually just multiply the LCD. Multiple LCD. If we consider all the denominator, number on the denominator is actually 7x and the y. So basically it's just because x and y are variable. I don't know their relationship with 7. Obviously, 7xy is the common denominator. So that's the LCD for all three of those. So we're going to multiply across the board. So that's 7xy multiply 1 over x plus 1 over y, and then also equal to 1 over 7 multiply 7xy. So when we do this, basically, obviously, going to distribute into it. So basically, when you distribute into it, obviously, this term will be canceled, this one here. And so this actually will cancel x. So we got 7y left over when we distribute it this way. Distributing this way, we got y going to be canceled out. And what we left is 7x. And here, when we multiply the right-hand side, basically we cancel the 7, then x, y left. So this seems to be a equation which still very daunting, and because we need to figure out integer, two integer, one is x, one is y. Those are all positive integers that satisfy that, 7x plus 7y equal to xy. Still, you totally have no clue. So, but what we observe is that, x, y, if we put those on the same side, we might be able to factor it. So basically, then let me just, we're going to be minus 7x and minus 7y on both sides so that they will be on the same side. Then it looks like 7x, xy minus 7x minus 7y equal to 0. So that's still not helpful. Then, but how do we, factor this into a, and how do we factor this into some way that might be useful. So if we do x minus 7 multiply y minus 7, actually it will produce all those 3 terms with extra term. So if we do that, if we file it, then basically, so this is the highlight. I'm going to change the color. So when we file this, so this is just a guess. We guess, this product will be useful. And then because this product will produce those 3 terms, when we file it, so the first term is xy, the second term is minus. So this is 7x. And xy minus 7x minus 7y. And then negative 7 multiply negative 7 going to be positive 49. So this one, so this equation compared to this equation actually differs by this extra 49. So basically, if I replace the left-hand side, left-hand side of those 3 variable terms with this factorization, I actually add an extra 49 on the left-hand side. So the right-hand side need to add a 49 at the same time. So basically, what I do basically, this is just a guess. So what I'm doing is that after I have this guess, I am doing that this equation, for this whole equation, I adding 49 on both sides. So this equation with 0 on this side will have 49 on the right-hand side alone, and there's going to be have an extra 49 here. Then this 4 term can be factored into this, x minus 7 and y minus 7 factored form. So basically, so this is the first step, which we already satisfying the, so the first step is rational equation. We actually need to, get rid of denominator. This is a very common sense thing. So for because for anyone doing the rational equation, the first thing usually is always doing that step. So there's no question on this one. And the real trick is here. The real trick is that this is hard to handle, but this factorization could cover 3 terms. And we just need an extra term to really achieve this factorization. In order to achieve this factorization, I need an extra 49 on both sides. So basically, it cannot be just on one side. If you're just adding 49 without balancing another one on the other side, it wouldn't work. So basically, this is the first meaningful step, which without question, because from here to here, that's natural. And this first one to the second one is not natural. This one is calculated move. This calculated move comes from the Simon's favorite trick, factorization, which is invented by a math lover in this community. And so we have his name honored. And so basically, he actually, thinks this is a good trick. So in order to fit 3 terms, we need an extra constant term. So the second term, after exploration, we find that 7 multiply 7 equal to 49. That's a good term to add. So once we did this, then basically we will go back to this. So this is the third step. So this is about x minus 7 multiply y minus 7 equal to 49, because here we have, obviously, this will equal to this product with 49, and the 49 on this here will inherit here. So right now we actually have this equation that, because this is an integer product makes it easy because we only need to consider factorization of the 49 as a number. So x minus 7 and the y minus 7, how many way we can, product to 49, and the x and the y has to be integer. So they actually belong to the integer domain. This is the integer domain. And so basically, that actually very easy to handle, because if X is the integer domain, Y is the integer domain. So basically the -7 still going to be integer and still has to be positive integer. You are not allowed to use the negative integer. So 49 has only limited way to factorize. So basically, 49 you can 1 multiply 49 or 7 multiply 7 or 49 multiply 1. So that's only 3 way. So we will just rotate between them and figure those all out. That became much easy. So basically, we can say X -7 equal to 1, for this one to match, let's say that match this factorization, the yellow one. So we actually has a pair of X -7 equal to 1, Y -7 going to be equal 49. And then this way, basically, X equal to, so we add 7 on both sides, X equal to 8, and the Y equal to add 7 on both sides, that's going to be 56. Then to fit this one, basically, it's actually, I'm going to use a different color. So basically, this one, the blue one, I'm going to use the blue color. So basically X -7 going to be equal to 7 and Y -7 also equal to 7. So this way, basically X equal to 14 and Y equal to 14. And that's quite obvious. And then the last one, let me use the, let me just use red, purple. Let me use the purple one. So this one, basically, let me try to use a purple color pen. And I think this is as close to purple as possible. So basically, and this one basically is just X -7 equal to 49 and the Y -7 going to be equal to 1. And that will get like X equal to 56 and Y equal to 8. So we can actually double check to see whether or not it's working. And so like this one different works, because 1 out of 14 plus 1 out of 14 equal to 1 out of 7. That's obviously working. And this one, let's say that 1 out of 8 and plus 1 out of 56. That's actually is equal to the LCD is actually 56. Then we need to multiply 7 and multiply 7 on both numerator and denominator. So that's 7 plus 1 equal to 8 over 56 equal to 1 out of 7. So it's actually checks. So obviously, X and Y is symmetric. So basically, if X equal to 8 and Y equal to 56 works, and X equal to 56, Y equal to 8 also works. So basically, given those information, this problem became solvable. Find the greatest possible value for 1 out of X. That's actually, and the greatest possible value of this is reciprocal one. So this must be 1 out of 8, because we have 1 out of 14 and 1 out of 56 and the 1 out of 8 as possible value of 1 out of X. And obviously, the smaller the denominator, the bigger the value. So 1 out of 6 biggest possible value is 1 out of 8. Then we need to find the value of X in terms of Y. Yeah. So value of X in terms of Y, basically, if you just use this way, reaching this step, basically, it's just we have to solve this way. So basically, X. 7x minus x 7. Let me do it the other way. So xy minus 7x equal to 7y. Then we need to find the value of x in terms of y. So we can factor out x, xy minus 7. So basically, x equal to 7y over y minus 7. So that's the way that you can find the value of x in terms of y. Then, but this one is actually not very useful, but you actually is useful in terms of like trying to use the Simon factorization this way. This way is the most efficient. And then it's trying to find the sum of the all possible value of x. Sum of all the possible value of x basically will be just, you know, is x has possible value of 8 and 14 and also has possible value of 56. So basically, you know, if you add those number up, not 65, 56. So this is actually 70, 78. So basically, if you add those up, it's going to be equal to 78. So that's the way you kind of solve this problem. And this problem, the solving of this problem is quite lengthy, and but it's very, very important. So this is, you know, a big explanation as a so you just have to be able to do this problem. And so basically, also on the second step, basically, you know, x actually in terms of the y, you actually can get that. So x equal to 7y over y minus 7. And this in turn basically is equal to 7 plus 49 over y minus 7. So how do you reach from this step to this step? Basically, you know, you can do this way, y minus 7, and then there's 7, and then you just trying to fit a y minus 7 here. When you fit y minus 7, basically you can get one integer out, because this type of the problem, you want to introduce something that has variable only on one side of the denominator or numerator. And then, because when you do this, you actually introduce a negative 47 or 49, then you actually have to plus 49 on the other side, because this term is extra. Then the first front part became 7, and then plus 49 over y minus 7. And because x has to be integer, x expressed in terms of y, and 7 is an integer, then 47 divided by y minus 7 is also an integer. So x has only limited way of doing it, very limited way of doing it. So basically 49 you can divide by 1. 49 divided by 1 will be 49. So if y minus 7 equal to 1, then y will be equal to 8. Then the other possibility is that 49, another factor is basically just 7. So y minus 7 equal to 7, then y will be equal to 14. And then the other possibility is that y minus 7 equal to 49. Then basically, it's going to be y equal to 56. So basically, if you express x in terms of y, and then trying to split it up with like a integer plus another fraction, which this fraction is actually has engaged in integer division. And integer division, so basically integer, the good part about the integer division is that it only has limited way that still can be in integer. So basically, these are the only 3 possible way. So basically, this is the way that you actually doing it, 2 different paths. So basically 2 different paths of doing this. One is the like factor it this way, express x in terms of the y, then take it apart along the integer, and each part is the integer. This addition part is the integer, and then the remaining division of fraction need to be integer. That way will, there's only limited way that you need to explore, and everything is very clear. Then the other way is just using Simon's trick and Simon's favorite trick, and that also works. So there are 2 ways of doing it. Just, you have to understand and master this trick. So let's keep on doing the next problem. And I think today's a lot of emphasis is on like, Simon's favorite trick, and also problem 3 that another method is you express x in terms of y, then trying to consider the limited way of integer division. So these are the key points you need to understand today. And also there are a lot of this type of the problem engaging the like factoring, a square minus b square factoring. Then also the other side basically is a integer. So there's only limited way to factor, then you can actually build the equation system to solve it. So these are quite important things. I don't think we actually have too much time left. We have 36 minutes left, and we still have a lot of to cover. So right now, let me just on the fast track, try to cover as much as possible. I hopefully will cover the whole chapter from 7.5 to 7. We still have 6 problems to cover. So let me cover it really quick. And so this one is just, so right now, I will just let you read the problem, and then I will try to solve it. And Eddie, can you try to read this problem?
Simplify the expression x to the power 3 y plus y for x equals 10. A 6-digit number is formed by repeating a 3-digit number. For example, 256,256 or 678,778, etc. Find the greatest common denominator of all numbers of this form.
Thank you. So this one basically is, x equal 10. So we just replace into it. That's, 10's cube, which is 1,000. So it's just, a 10 cube y plus y equal to 1,000, y plus y equal to 1,001 y. So this is the expressions that this is the simplified way. So these number actually can always be expressed by this way, because for example, this number is repeating 3 digit, which has total of 6 digit. It's actually 256 multiply 1,001. So this is actually 678 multiply 1,001. And so obviously these number has no common denominator because this is a class of numbers that it could be anything. So, you know, it could be a prime. You can just find another 3-digit prime. 3-digit primes, there are a lot of those. For example, that maybe 103 is a prime, 107 is another prime. And so if you use those two prime, basically, you know, then there's no way you can have a common divisor out of those. So the only common divisor is in this. And obviously, you know, this form of integer always have 1001 as a divisor. So basically 1001 is the GCD, the greatest common divisor of all these numbers in this form. So that's the answer for problem B. Okay, let me get to 7, 5. And Angela, would you try to read this problem?
Problem 7.5. Let n be the least common multiple of 7 and 8. Find the value of n. Find the greatest integer less than 1000 over n. And what is the greatest 3-digit number divisible by both 7 and 8?
Thank you. So this problem, because 7 and 8 are co-prime, and this is the least common multiple, so it has to be the product of all their prime factor in the minimum form. So basically, you know, this is 7 equal to 7 and 8 equal actually to Q. And just consider like prime by prime, you need a 7 to the first. You also need to so the max, the largest index for prime 2 is 3. So you also need 2 to the third power. So it has to be 56. So this first problem is very simple. If you do it, this is the most formal way. If you don't go most formal way, that if you know, anyone has the gut feeling to tell it's 56, then we need to find the greatest integer less than 1000 divided by n. And so because n is 56, so basically 1000 divided by 56, let's see that, you know, how many number we can multiply up to be a little bit less than 1000, but not more than 1000. This is just, you know, integer division. Integer division, you have quotient, then remainder. So remainder need to be less than 56. So you will get this value. So this is very easy. So 1 multiply 56, you got 44. And then this one, I think maybe 8 or maybe 7. Let's try into 7. $392, so that's actually 8. This 13 minus 9 equal to 4, 48. So the remainder 48. So basically looks like the greatest integer less than, you know, 1000 divided by the n is, because this one division actually has some remainder. So basically, you know, it's actually 17 and 48 over 56. So this fraction, the greater integer less than this fraction is just 17. So it's very obvious. So then this is C. And C basically is asking what is the greatest 3-digit number divisible by both 7 and 8. So basically we just need to multiply this up to 17 because, you know, any multiple of 56 is divisible by both 7 and 8. And we have found out that 1000, number 1000 can fit 17 of 56 with 48 as remainder. So basically that value going to be 56 multiply 17. So that's going to be 952. So 952, that's the greatest 3-digit number divisible by both 7 and 8. So let's go to the next one. Next one, Blair, would you try to read this problem?
Okay. A. Find the greatest common divisor of all perfect squares that are multiples of 7. B. Find the largest 4-digit perfect square that is a multiple of 7. C. Find the smallest 4-digit perfect square that is a multiple of 7. And D. How many 4-digit perfect squares are multiples of 7?
Thank you. So this problem is also extremely important. Let's try to figure out how to do this. So first is that perfect square that multiple of 7. So basically, a perfect square is just, prime with even index. So, a perfect square, if you factor it out, for example, if you have a number n, that is the, number series result we already learned. So if an n is a perfect square, it has to be in this form. P, like let's say that 2p1 2i1, which I is any integer, and then basically it's a even, it's an even integer. So this has to be in a p2 prime 2 to the i2, so something like that until like pk and to multiply I to the k. So it's in this type of the format. Since it has a prime already is 7, so basically, it need to be like 7 square. So basically, all the GCD all prime with multiple of 7. So this 7 square is a, greatest common divisor, and it has to be at least contain another factor of 7. So it's 7 square. It doesn't need to have more, because 7 square itself actually satisfy the need. So 7 square is equal to 49. That actually satisfied the whole statement. It is a perfect square. First, it is perfect square. Second, it is multiple of 7. So basically, GCD just means that greatest common divisor. So this is the number that satisfy. And so if you have a group of numbers, so greatest common divisor cannot be bigger than any one of those. So basically 49 is already a number in that set. So 49 has to be divisible by all those forms, and 49 is one of those. So basically 49 is the greatest common divisor. So the first problem is done. Then trying to solve the second problem is trying to find the largest 4-digit perfect square that is multiple of 7. So the second thing is just trying to fit another prime or another factor which is a perfect square into the, so largest 4-digit number basically is 9999. So basically, we can try to divide by 49 to see how many of 49 we can fit. Then basically that's going to get 2 of those. That's 98. So 19 you can fit 0. Then this you can fit 4. 196 remainder is 3. So basically, you know, if you're trying to fit as many 49 as possible to the largest possible 4-digit number, you can fit 204 with 3 as remainder. So basically, and this need to be the product, another product upon 49 to make a complete square. And so 3-digit complete square, we know that 196 is one of those. Basically, you know, we know that, after 81, 100, then 121, that's 11 square. Then 144 is 12 square. And 169 is actually 13 square. And 196 is 14 square. So basically, because the largest 4-digit perfect square need to be has perfect square factor. 47 is a perfect square. Then the other portion also need to be perfect square, and the largest possible out there less than 204 is 196. So basically multiply 196. That's going to be largest 4-digit perfect square. That is multiple of it. And we can actually factorize the whole thing. So this is actually 7 square multiply, and this actually is equal to 4 multiply 49, which is equal to 7 square multiply 2 square multiply 7 square, which going to be equal to 4 multiplies is 4. So 2 actually going to be 98. This is 98 square. So basically, so we actually have a clear path that we know that this number is actually 98 square. Yeah. So 98 square. So what is, so it's asking for the largest 4-digit square is multiple of 7, and that number is actually 98 square. Then we just need to calculate out. Calculate out, you can do direct multiplication, or you can use certain trick. It's still be able to do that. 98 actually 100 minus 2 square. So if you use this trick, it's actually equal to 10,000 minus, this is 2AB. So 2 multiply 100 multiply 2. Then we'll plus 4. So basically this is actually 400. So this is actually 10,000 minus 400 is 9,600 plus 4. So 9,604. So this is the result for this one. So basically, like the algebra trick is not just useful in solving the problem. Sometimes calculation, especially if the number is close to an integer, a big integer, like even integer like 100, it actually could help you to multiply a little bit faster and more accurately. Then let's try to do problem C. Find the smallest 4-digit perfect square that is a multiple of 7. So the smallest possible 4-digit number is actually 1,000. So let's see how many 1,000, for 1,000, how many of like 49 we can fit into it. So let's say 49, that's going to be 2 multiply 49, 98. Then we got 20. And 20 we can fit 0. So it's 20. And then 20 over 49. So basically, 1,000 divided by 49 is just equal to this number. So because we want this number to be bigger than 1,000, so we actually not rounding down, we actually rounding up. So basically we can say that the least 4,000 or the least 4-digit number that has a 49 as a factor is actually 21 multiply 49. But 21 is not a complete square. The next complete square is actually 25. So basically, you know, it has to be like 25 multiply 49. That's going to be the result. And 29 multiply 49 actually is equal to 5 square multiply 7 square, which is equal to 35 square. And the 35 square. So 35 square, you actually has a trick to multiply it. 35 square is just 1225, because actually the for the complete square, like, you know, 15 square, 25 square, and 35 square, 45 square, and 55 square, 65 square, 75 square, 85 square, and the 95 square. They are all very easy to calculate. It's just they always end up with 25 as the last digit. Then the up digit is actually 1. This is 1 multiply 2 equal to 2. This is actually 2 multiply 3. So this is 625. This is actually 1225. This is 2025. 3025. 4225. 5625. 7225. This is 9025. So basically this type of the, you know, 2-digit number end with 5 is very easy to square. So basically, you know, if you find this, actually you can just do it by mental math. You don't have to calculate with a draft paper. Then it's asking how many 4-digit per square are multiple of 7. So basically, you know, we actually find that it's actually 49, and then how many perfect square? It's asking for the perfect square. So basically, you are multiplying, like, you know, it's 5 multiply 7 square, the first one, the least one. And the largest one is actually 14 multiply 7 square. That's the largest one. So, you know, it's in this form. So basically, it's in this form. So there are not a lot of those. So basically the next one, imagine you actually dealing with this one, it has to be a perfect square. The next one is actually 7 multiplies 7, 6 multiplies 7 squared. The next one is going to be 7 multiplies 7 squared. So basically, you know, it's just counting between 5 and the 14. So 14 minus 5 equal to 9, 9 plus 1, because it's a inclusive counting. So you actually have 10 of those. So that's the, you know, that's the way you can handle this problem. So this type of the problem is that, you know, basically it's 49n square, which is, you know, if you, I didn't do it this way, but this way is actually a very good way that, you know, if you express, because the other number need to be also a complete square. So given that fact, you can actually, you know, express this middle number that satisfy all the description as 49n square. And then you can actually divide 49 on both sides, and basically, you know, you can put a brace. So this is basically, you know, put the left limit and right limit on it, and then with a square, then you square root of it. You do square root, then basically you actually got 10. So either way, it's fine. So that's kind of the way that you can manipulate this type of the problem and get an answer. Let's try to do this problem. And this is a long one. Will, could you try to read this one?
Anna owns marbles that are either blue, green, or red. She has 7/5 as many blue marbles as green marbles. Excuse me. Thank.
Will, you actually muted yourself. We cannot hear you. Okay, looks like Will is having technical difficulty. He muted himself. So let me just read the remaining.
Oh, I'm
So-
back.
Oh,
Sorry.
you're back. Okay, no problem. You
I
can
just
keep reading.
I was just sneezing in the middle of my reading. Sorry.
Oh, okay, no problem.
Get a napkin. And had 2/7 as many green marbles as red marbles.
Uh-huh.
Let B, G, and R be the number of it is blue, green, and red marbles respectively. In terms of G, how many blue marbles does Anna own? So
I think we actually don't have time for you to solve it. I think you can just read every problem and then we'll try to solve it. Will? Okay, let me just try to begin to solve it. So basically, this part is that, you know, we just have to read all the problem very carefully. Has 7/5 as many blue as green marble. So basically the blue one is 7/5 of the green, because if you read has twice as many, you know, blue marble. If you twice, you actually need to multiply 2. So you 7/5, you actually, you know, just multiply 7/5. So here is that you have, this is, you know, has 2/7 as many green marble as red marble. If you say 1/2 as many, so basically, you know, this is actually, you have to multiply 1/2, and then this is basically is, you know, so the green is actually equal to 7, is actually 2/7 as the red. So basically, this is the way that you can draw the diagram. And this is actually very, very hard to read. So I have a trick for you to construct the relationship between them, because we actually have 3 types of the marble: blue, green, and the red. So how do we make a grand picture about how their relationship is? Actually, you can use a table to do it, and also doing the ratio. So how do we convert this into a ratio? So basically, let's divide G on both sides. If we divide G on both sides, it's actually B over G equal to 7/5. So B G is 7/5. And so this is the first line of information we can put into a table. And this is actually, you know, the ratio conversion and connection table if you have to deal with multi-ratio, because multiple proportion. So ratio basically is the comparison of 2 quantities, and proportion is just equation of ratios. So basically we have 2 equation of ratio. We want to link them together. That's the way to do it. And then basically, you know, this is just, you divide R on both sides, you get G over R equals 2/7. So G over R equal to 2/7. So basically, and so obviously the link to connect those 3 quantity together is the common data we have on the green. And the green basically has a 5 and a 2. 5 and a 2, we just have to find the LCD. And LCD of 5 and 2 is 10. So we just multiply up to 10. So for this, for 2 to scale up to 10, we have to scale 7 up to 5 because that's multiply 5 relationship, multiply 5. So there's 35. Then for 2 to scale up to 10, so that's need to multiply 2. This is multiply 2. So 2 multiply 7 equal to 14. So basically, this is the way that you can get a grand ratio between those. So these 3 problems are extremely easy. I kind of just going to skip it because this is actually the difficult part. So how you solve the difficult part, you use a multiple ratio table, which, you know, each pair is just one data out there. And this is another pair of the ratio. And you find the common data, which is visible on all the same column everywhere. And this is obviously the common data links them together and find the LCD, then scale up on the other one, you will be able to find a common ratio, which, you know, link all the data together. So here, basically, we need to find 3 natural number BGR, which B equal to capital B equal to Bm and capital G equal to Gn and capital R equal to Rn. And basically, you know, the BGR, B is equal to, so B equal to 14 and the G equal to 10 and the R equal to 35. So that's the way you do it. Then we're trying to figure out, right, the total number of the marble in terms of N. So basically, you know, total number basically is just adding them together. You're adding Bm plus Gm plus Rn, which BGR you just plug in, basically equal to 14 n plus 10 n plus 35 n, which is equal to, this is 24 plus 35, going to be 59 n. So 59 n is our answer. Then we need to find the smallest possible number of marble Anna can own. And obviously, when the smallest one is n equal to 1, because, you know, if you say n equal to 0, that's meaningless. It's degenerated, the problem. Then the least possible is just 59. So let's check our result here. Yeah, so this type of the problem you kind of just expressing this way. And it actually has a lot of this kind of reasoning. I don't find this very useful. The way I doing multiple ratio problem, I always use a table. Table is way more visible, way more easy to link data together. And this is actually not a good form I like. But anyway, I think I did better on this problem than the explanation did. So let's go for next one. Next one, Xinlai, could you try to read this problem?
Okay, so let n equal let n equal ABC be a positive 3-digit integer that is equal to the sum AB plus BA plus CA plus BC plus CB, 6 of positive 2-digit integers. If 26A equals 4B plus 7C, what is the largest possible value of A?
Yes. Okay, let me try to explain and solve this problem. So this problem basically, you know, if you have in this format, basically, you know, you actually is able to write, you know, n basically is equal to 100A plus 10B plus C. And this one basically is just 10A plus B. This is 10B plus A. This is 10A plus C. This is 10C plus A. This is 10B plus C. This is 10C plus B. So basically, you know, if you add those together, let's try to observe that, you know, 10A, how many 10A do we have? We have 2 of 10A. And then we have 2 of the 1A. So basically, you actually adding them together for A on the right-hand side, you actually have 22A. We actually get rid of like 1, 2, 3, 4, 10. You add all together, you have 12 10. So one, because each number generate 2 10, you have 6 number. And A occupy 4 position and is 22. Then B is actually also occupy 4 position, 1B, 10B, 10B, and 1B. So basically also at 22B. It's all symmetric. So basically it's going to be 22C. So basically, you know, we are able to like express this. So then this type of problem, so integer related problem, usually you just want to like, you know, keep both sides positive. Keep both sides positive basically looks like to combine A on one side minus 22A is our best interest, which will generate 78A. And then if we combine B on one side, it's actually best to minus 10B on both sides, because that will transfer this to the other side, because we want both sides to be positive. And so that will get us to equals 12B. And then we combine C on both sides, we just minus C will be equal to plus 21C. And this obviously all the number is divisible by 3. So basically this is actually equal to 4B plus 7C. We just going to multiply 1/3 on both sides, because we notice that every coefficient is 3 multiple. So this is actually going to 26A. So we actually, you know, figure out how do we achieve this. Actually, this one is actually, you know, we derive this information by using correct representation of this data, and just do the algebra. We are able to figure out this one. And then it's asking what is the largest possible value of A. So largest possible value of A, we trying to see, you know, how large this side could be. This side is positive, and we know that B and the C is actually greater, and this is actually, you know, P positive number. So basically AB, so BC, all of them need to be greater than 1, and they also need to be less than 9. So let's say that BC are both 9. That's the largest possible value. So B, let's say B equal to C equal to 9. Then basically this is just, you know, 4 multiplying 9 plus 7 multiplying 9, which is equal to, we can factor out the 9. So 9 multiply 4 plus 7, which is 11. So 99. So 99 is the largest possible right-hand side we can achieve. So basically, what we are doing is that 99 divided by 26, that's going to be 3, because you cannot fit a 4. 4 will be greater than 100. So 78 with remainder of 21. So basically, you know, the largest possible A is just equal to 3. So largest possible A equal to 3, then basically what we get is that 3 multiply 26. 3 multiply 26 equals 78. 78 equal to 4B plus 7C. So basically, it's asking what is the largest possible for the N. So basically, you know, we're trying to get A largest possible. Then after A is largest one, we need to get a B to the largest one. And A, the largest one, obviously is 3 and be the largest one, you know, could be 9. So let's just give that a try. So 78 equal to 4 multiplying 9 plus 7c to see if it works. And 4 multiplying 9 is 36. So 78 minus 36 equal to 42. So 42. So basically that just means that 7c equal to 42, c equals to 6. So b going to equal to 9 and a equal to 3. So basically 396 is the largest possible value we can get. And that's, we can say it with very high confidence. So let's try to check the answer. Yeah, in the end, it is 396. So basically this type of the number theory problem, you know, you just express this problem in the right way, then do simplification, then trying to judge side by side with the limitation. So why do we keep both sides positive? Because if one side is positive, you actually have to regard all the limitation you come with the positivity, and then that will help you to limit the possibility you can have. So like integer problem, a lot of time you actually do not have the enough equation to solve it. But basically integer constrict, integer limitation, integer constriction is one of very strong constrictive conditions that you can have, because you know, with integer solution, your possible solution is only limited. You have finite possible ways. So we just want to take advantage of those limited possible ways to explore it. And then we actually is able to hit the solution. So let's try to do the last problem we're going to explain today. Eddie, could you try to read this problem?
Find the total number of positive 4-digit palindromes. Find the average thousandth digit of all positive 4-digit palindromes. Find the average hundredth digit of all positive 4-digit palindromes. Find the average 10 digits of all positive 4-digit palindromes. Find the average units digit of all positive 4-digit palindromes. Find the average of all positive 4-digit palindromes. Find the sum of all positive 4-digit palindromes.
Thank you. So this actually is a sequential problem trying to guide us toward the final goal. So how do we find the sum of all positive 4-digit palindromes? And it's actually not an easy problem, but we just trying to solve it by a sequence of the problems that make it easy. So the first problem is extremely easy. We already solved that before, that total number of all positive 4-digit palindromes is actually, you know, it's in the format of A, B, B, A. So basically, you know, this has 9 possibilities. This has 10 possibility. 9 multiplied 10 equals 90. So we have 90 possible ways, total number of positive 4-digit palindromes. Then we try to find the average 1,000 digit of all the 4-digit palindromes. So the 1,000 digit, basically, we can range them from 1 all the way to 9. The average of 1,000 digit is actually, you know, because one digit are interpreting to 1,000 and, you know, 2,000, but we just looking at the digit itself, and the average is obviously is 5, because this is actually 1 all the way to 9. It's just adding 1, 2, 3, 4 all the way to 9, then divide by 9. So it's just adding 1 all the way to 9 is 45. Then divide by 9 equal to 5. So basically 5 is the average of the 1,000 digit. And then it's asking for the unit digit because 1,000 digit and unit digit has symmetry. So it's going to be 5 also. Then trying to find the average of 100 digit. 100 digit, you have 10 possibility. It starts with 0, 1, all the way to 9. When you adding them up, it's going to be 45. And divide by the possible data sample, that's 10, which is 4.5. So basically this is 4.5. And this is also 4.5 because 100's position and 10's position are has symmetry. Then we try to find the average of all positive 4-digit palindromes. So for the 1,000 digit is basically 5. So it's for 5,000. The average going to be average of all those digits because 5 is on the 1,000 is 5,000 plus. Then this is the 100. 100 basically is 4.5 multiplied 100 is 450. Then on the tens, it's 4.5. 4.5 need multiply 10, that's plus 45. Then the last digit is 5. So basically that is the average. Because we are averaging on every position and you have 4 positions, when you're adding up all the positions, then basically the average of every position. So that reason behind is very simple. So this is actually going to be at 550. And 50 plus this is going to be 500. 500 plus 5,000 is 5,500. So 5,500 is the average of all those 4-digit palindromes. Then it's need to find the sum. The sum of those is just average multiplied data count. Count is 90. So this is 55 multiplied 9. Then we will add 3 0 up. This is 2 0, this is 1 0. We don't have to, do calculation with trailing 0. We can finish calculations and adding the zeros up, back up. So this is 45 and 45, 495. So 495 is leading 3-digit, then we need to pad 3 0 up. So the final answer is this one. So the sum of all positive 4-digit palindrome is 495,000. So let's check the result. Yeah, so that is the result. Okay, so time is up for today, and that's all the questions we cover. And thank you, everyone. Have a nice evening. Bye-bye.
Thank you.
Bye.
Bye.
Thank you.